his PhD thesis on the topic astrophysics. Publicly defend his PhD thesis. Jordan Van Beeck, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give you the floor.
Okay. Let's see. Can everybody hear me? Just to make sure. Also on the online stream. Okay, I see Jim now. Great. Let me just put this on full screen. Okay. So, good afternoon and good whatever part of the day you are while watching online. Welcome to my defense on the astroseismology of Kepler B stars, and then specifically regarding internal magnetism and nonlinear mode coupling, which was supervised by my promoters, Connie Aerts, Tim van Holst, and Dominic Bowman. So this is a lot of jargon in this title, and I'll try to explain you the words throughout this presentation so that you can try to get a better feeling of what I did the past 4 years. So the menu for today is we start with a long buffet of appetizers. Then we go on to a main course and then have a little room over for dessert and coffee. The first appetizer that we're gonna tackle is the question what a star is. Now, if you'd asked this question 100 years ago to a famous astronomer called Eddington, he would probably have said that a star is a fundamentally simple object. Now that we have a bit better measuring capabilities, we might say that these stars are quite complex spheres, or maybe not even spheres, depending on the rotation, of plasma, or specifically a gas that has ionized components. And this plasma sphere has a lot of complex processes going on inside of it. A good example is this star that you can see here on the screen. This is our sun. And for an example of an ongoing problem in the field of solar physics is the explanation of why the layer just outside the surface of the sun is hotter than the surface of the sun itself. So these very complex stars, very complex objects called stars are quite difficult to study. So why would we study them at all? Well, so why is the study of stars in fact important, right? It turns out that these complex processes that go on inside these stars are producing a lot of the elements that we can find in our universe. Namely, they produce all of the elements inside of their, inside, but up to the iron isotopes. And therefore, during their lifetime, and therefore can also be looked at as some cosmic factory, or actually, in fact, a recycling factory of these elements, and then also enrich the universe. And without these stars, we would in fact not exist. We would not be here. There would be no Earth. There would be no solar system. So I hope you agree with me that the studying of stars is useful. We want to know what is going on inside of these giant bulbs of plasma, light bulbs, let's say. So when astronomers study stars, there's one thing that astronomers love, and that is putting things in boxes. And so we also put stars in specific boxes, or we classify them. And one way of doing so is by putting them on the Hertzsprung-Russell diagram, where you have your surface temperature, the temperature of the surface of your star on the x-axis, and you have the amount of light they emit, typically, or the luminosity on the y-axis. And you can see that these stars are actually grouped on that Hertzsprung-Russell diagram, and a specific group that is very important is the so-called main sequence. And these are stars that, in fact, have hydrogen fusion processes going on inside their core. So inside their core, the temperatures and the conditions are just right to make sure that hydrogen gets converted into helium isotopes. Now, this is an important group because the main sequence is where 90% of the stars spend their lives. In fact, our sun is right there, approximately. In this thesis, we don't focus on the entire main sequence, but we specifically focus on the B stars on the main sequence, which is the hotter and more luminous end. And the very important process, the very important hydrogen fusion process that goes on inside the core of these specific B stars is the so-called a catalytic cycle, called the CNO cycle, the carbon, nitrogen, oxygen cycle. And basically what happens is that you add a hydrogen, and through a slew of reactions, which are shown here, you get out a specific helium isotope, helium core, in fact, and during this process, the carbon, nitrogen, and oxygen isotopes are not consumed. They are used catalytically. So this might be a bit esoteric. So I always like to compare that catalytic processes to what you would use while driving, well, passively. You have a catalytic converter on your exhaust pipe. And in principle, the catalysis process is similar, but the conditions are very different. Of course, I hope that there's no hydrogen fusion processes going on in your catalytic converter. So there's a lot of energy being produced by this core hydrogen fusion. And now we have this enormous energy production, but now it also has to go somewhere, right? And to do that, we can maybe make an analogy, to study how this energy is transported outside of your star. We can maybe make an analogy with the boiling of a pot of water. So in the core, you have your hydrogen fusion processes, and these can be thought of as the heating source or your heater on this picture. Then, of course, there are three ways to transport energy. There's conduction, which is not that important for stars, the conditions of the stellar interior in general. Then there is radiation, so this is emitting heat through light. And this is important, this radiative transport in the outer envelope of these B stars. And when radiation is, radiation, of course, is dependent on how much of these light photons how much they are absorbed and scattered throughout your stellar interior. And the way that is measured is in terms of a specific fudge factor, a opacity, which is a measure for the absorbing power of your internal medium with regards to this radiative transport. So if the opacity is high, this means that your transport by radiation is not very efficient. So in those cases where this transport is not efficient enough to transport away all of the generated energy, you would have to go to the final phase of, final potential transport process for energy inside your star, namely convection. And this can really be thought of as analogous to your boiling water. So your hot water gets hot on the bottom of your pan due to your heating source, then it starts to rise and the cold water starts to go down, and this convective motion then can be thought of, this is convection, this boiling process. So this also happens in the core of these B stars, and it is very efficient at mixing the entire layer. So these the specific cores can be thought of as very well mixed. Now, the surface of this boiling pot of water is not straight. It's quite turbulent, in fact. We have a lot of bubbling going on. And this bubbling can maybe be thought of as an additional sort of mixing process. And in stars, this also happens, and at the core of your at the edge of the core. So you have these plumes of material that are convecting upwards and then shoot out of the core and come back into the core, transporting material, in this case hydrogen, into your core, which then resupplies the core with additional fuel for your heater, for your hydrogen fusion reactions. This means that, of course, when you have more fuel, you can burn for a longer time, and therefore you change your lifetime and also change the way you evolve. So this core boundary layer is in fact quite important. Okay. So when we try to simulate all of these inherently three-dimensional processes, it takes a lot of computing power, and it is right now quite impossible to simulate a three-dimensional model of such a star for its entire lifetime, for very long times. So what we do is make some simplifications, and in this case, we revert to one-dimensional simulations. So we look at what is happening with the properties of a star along a line. For example, this line here in black. So this is, of course, under the assumption that your star is, in fact, spherically symmetric. This means that whatever way you point your line from core to surface, the variation of properties is in principle the same. Well, is the same in our assumption. So an example, here on the x-axis, you see the variation of the this is from core all the way up to the radial coordinate from the core all the way up to the surface. And on the y-axis, you see a measurement of how efficient the mixing is happening inside of these stars. Mind you, this is on a log scale, so if you go up by 1, the amount of mixing in principle is multiplied by 10. So now that we've gotten some insight into how a simplistic model of the inside of such a B star looks like, we might just wonder how we can actually verify that, right? How do we peek inside of these stars? And very important for that, peeking inside of the star was space missions, so space telescope missions, such as the Kepler Space Telescope. And this specific Kepler Space Telescope was in fact created to look at how planets revolving around stars other than our sun diminish the light of their stars. So we have to look at them for a very long time so we can very precisely obtain the period with which they revolve around their stars. And the stars that they were looking at were therefore mainly stars like our sun, which are expected to have such planets revolving around them. However, Kepler also looked at more luminous and heavier stars, such as our B stars. Only a few of them, unfortunately. But this means that we also have very good data for 4 years long of these stars. And what we then can do is, for example, look at how this brightness of these stars relatively varies over time. And on the left-hand side, you can, for example, see the variation in relative brightness for the entire 4 years, and a zoom in on the right. So how do we explain these variations in these specific B stars? Well, one explanation is by means of astroseismology. So this is our next course on your appetizer buffet, where, well, we can split that up into 2 words. Astroseismology, we can say that the first part of the word is made up by aster, which is the Greek for star. And seismology then, of course, refers to the study of waves inside a specific medium that can be used to determine the properties of that medium and any processes that go on inside them. For example, how the use of earthquakes to study the interior of our Earth. Now, of course, when we put these together, we just use waves that propagate inside stars to find out what is happening inside of these stars. And for our purpose, so we are mainly interested in these B stars. They have two main types of waves. There are many more waves that can propagate inside of such stars, but the main types of waves are the gravity waves, or the pressure and the pressure waves. And the pressure waves, well, we're not talking about traveling waves specifically. We are talking about waves that are reflected at specific boundaries, and these reflections then form a pattern, of which you can see an example on the figure here, and this we call standing waves. So pressure, when you form these standing waves, we call them also modes. And these pressure modes these pressure waves, in fact, are also known as sound waves. So these are the waves you are hearing right now. But of more importance are the gravity modes, which are mainly sensitive to this core boundary region where this surface layer is, so where you can determine how long your star is. And an example of that can also be found on Earth, where you have a nice picture of some gravity modes or gravity waves in the air here. Again, astronomers like to put things in boxes. So we also like to put stellar oscillations in boxes. Specifically, we characterize stellar oscillations in terms of quantum numbers. And there are 3 quantum numbers that are of importance. We have the spherical degree L, which is the number of white lines you can see on this picture that do not go through the poles. So if you count with me, there are 3 of these white lines. And of course, the red areas on this picture are areas that are periodically heating up, that are heating up right now and then will cool down later in a periodic way. And then the blue areas are cooling down right now and he will heat up later on. The white zones are nodes or nodal lines that do not heat up due to this one specific mode, gravity mode, in fact. So the spherical degree these nodal lines not through the pole, whereas the azimuthal order is the amount of nodal lines that do grow through the poles on the surface. And then if we look inside, we can also take a look at how many nodal lines, or actually, in fact, in 3 dimensions, these are nodal surfaces we can encounter while going from the core all the way up to the surface. And when we count that number and take the absolute value, we get 9 for the specific oscillation. And these are then the radial, this 9 is then the radial order of that mode, or So, however, stars are typically not pulsating in one mode, but then they tend to have multiple of these modes going on at the same time. And this then produces a quite complex pattern, as you can see on the picture here. And in order to unravel that pattern, we can use a mathematical technique called a Fourier transform. And what this does is then obtain you a measure of these of the frequencies of these individual modes, which are then shown on the x-axis in this figure, as well as the amplitude of these modes. And these amplitudes are then how much they contribute to the difference in relative brightness due to a specific, per specific mode. For gravity modes, we then also look at so we have now characterized the properties of these modes. So what do we now do with them, with these properties? Well, we look for patterns. And for gravity modes, the main diagnostic that we look at is the so-called period spacing pattern, which are the periods, or 1 over the frequency, of the modes that have constant L and M, so for example 1 and 1, as well as a consecutive N. So from left to right on this diagram, the N increases for each mode by 1. And then the values that you can see here on these on the y-axis is in fact the difference in periods between these consecutive modes in seconds. Now these patterns differ depending on the medium through which the stars, through which the waves propagate and the stars propagate. So, for example, if the medium you are considering is rotating at a different rate, so let's consider that we have a star that is rotating as a whole, not differentially rotating. So for a non-rotating star, one might then obtain a pattern that looks like this blue pattern. And if we crank up the rotation, the pattern shortens, and it also gets tilted more and more. So what is also of importance in these specific stars is the buoyancy frequency, which is the natural frequency at which your well, a gas element would rise up and down in a medium that is, well, not convective. So this is quite important because it determines also the maximal frequency at which you would have the maximum frequency at which you can expect a gravity wave to or gravity mode to propagate inside your star. And there are several contributions. One is due to composition, one is due to the structure of your star. But what is important, for example, is that they define where your mode can propagate. For example, this mode can propagate all the way up to here, whereas this mode would, if it was excited, not propagate except for this specific part of your star. And where this buoyancy frequency drops down below zero, this is exactly where you would have these convection zones. Finally, we have one more tough part of the cookie in our appetizers. That is, how do we actually get the modes to be, well, how are these modes in fact excited? How do we have modes inside of these stars? And well, that can be explained by the opacity mechanism, the kappa opacity mechanism in these B stars, where you have, well, what you need, of course, is that there's a net energy inflow to your mode. So what this kappa opacity mechanism does is, well, each time a mode passes by a specific medium, you have a compressive cycle, and you have, well, it compresses the medium, and when it goes away, it relaxes the medium. So when it compresses, what you need to do is make sure that while you compress, you add heat to the local medium where you're compressing. And if you do that, you can then start to add energy to your propagating wave. And this is in fact what happens due to the kappa mechanism. It's the heat tension mechanism. And this would happen in these specific layers very close to the surface of your star, where you have hydrogen. For B stars, in fact, this is not hydrogen, but there are iron-like isotopes that are missing some electrons. They are ionized, and these transitions then help you perform exactly that. They help you perform the mode driving. So now we've talked about the first part of the title. So I think we're done with the appetizers. What about now the other words in our title, the internal magnetism and the nonlinear mode coupling? So what about the actual work that was done during my thesis? So my PhD project revolved around studying these gravity modes that are propagating in these B stars on the main sequence. And specifically, we then looked at how the gravity modes are affected by the effects of internal magnetic field or by nonlinear energy exchange among the modes or nonlinear mode coupling. And to do that, we are missing one specific ingredient for our main course, the observational incentives. Basically, why would we want to study internal magnetism or nonlinear mode coupling at all if there is no observational evidence for it, right? So what we did is then look at pulsating B stars on the main sequence, known as slowly pulsating B stars or SPB stars. And we looked at these variations of brightness over the 4 years of time that Kepler was peaking at them, and subjected these variation curves to 5 signal processing strategies, or also called pre-binding strategies, to then obtain a robust characterization of these parameters in your after subjecting them to a Fourier analysis. So we want to know what are the amplitudes of these individual modes and what are their frequencies. And if we do that by these, if we let these 5 signal processing strategies do their thing, we obtain 5 different models for this specific star's variability curve, in fact. And these 5 different models can agree and they cannot agree. So if we look at the graph here, that is shown on the right, you can see how much they agree with each other, and also how much they can explain, how well they can explain, in fact, the variability that is observed by Kepler. And for 50% of these stars, which are called the high FSV stars, sorry, I also put them in boxes. I'm also an astronomer, I guess. These high FSV stars, they are well represented by the techniques that we use to model them. So that's a very good thing, of course. But now what we do with these 5 models is combine the information in them to then obtain a specific consistent model for the variability of these stars. Once we have these consistent models for the variability of the stars, we go one step further and we search for specific combinations of 3 signals. And these specific combinations of 3 signals have parameters that need to fulfill specific conditions. Specifically, we have that their frequency difference, so this is the mode frequency shown on the x-axis here, that their frequency difference should be approximately 0, otherwise known as that they should be approximately resonant, and their phases, another parameter that we can obtain from these models for the variability, should also have some integer multiple of some integer multiple of pi over 2, which was a criterion that was inspired by earlier literature. And when you do that, when you look for these specific combinations of 3 signals, you find that there are many of these specific combinations that have these conditions satisfied. And in fact, you can see on the right-hand side, all of these combinations that we find in these specific set of stars, for the specific set of stars. That leads us to conclude that these specific stars are, in fact, nonlinear oscillators, because these specific combinations of 3 signals or modes can potentially be described by theory. So there is a link to there's an incentive to look at the theory to try to obtain a good model for what is happening with these specific sets of 3 combinations of modes. However, these models are also useful for other things. For example, we can use them to look at the detection of magnetic fields inside stars. Now, magnetic fields have been detected. There were many magnetic fields that were detected on the surfaces of such stars. But one of the issues that we're having, is that these measurements that we use to detect these magnetic fields cannot penetrate the surface. So, how can we peek inside? Well, we can look at how they affect the modes. Specifically, we can look at how they affect the gravity modes, which are then, of course, specifically sensitive to the near core region. And what we do in my third chapter of my thesis is look at how the frequencies of these specific modes are affected by the internal magnetic fields. And we did that while also considering the effect of fast rotation simultaneously. And this, at the time, was the first time such a study was done, while we also consider the influence of specific model parameters. So, for example, we look at how this is affected by the evolutionary stage, okay? Also the mass, and the mixing, the rotation rate, and the field strength. So very quickly, we look at what is happening inside of this envelope. We look at how this mixing level affects this, these specific shifts due to internal magnetic fields. And we have two effects. We have a sawtooth-like pattern that is appearing here. And if you crank up the mixing, this sawtooth-like pattern disappears, and you are left with some slope change. And these effects were then found to be detectable by space photometry when we compare it, for example, with typical frequency resolutions of Kepler. Finally, in the last part of my thesis, we look at how how gravity modes exchange energy due to a nonlinear mode coupling process. And to do that, we derive the theory. We derive the aptly called amplitude equations that describe how amplitudes are varying over time due to this mode coupling. And one of the solutions you can obtain in these sets of equations are so-called time-independent solutions. And what you can see here on the right-hand side is one of these numerical solutions of these sets of amplitude equations for arbitrary starting conditions that converge onto a specific time-independent solution. And these amplitude equations can then describe what is happening inside of these combinations of three signals, potentially. But in order to do that, we want to make sure that we have a valid and also a valid solution that is time independent and which can also be sustain some small change in the parameters without diverging away from that stable from that time independent solution. And when we did that, we obtained more stringent validity criteria and stability criteria than in literature, which is shown here on the right-hand side. But what is most important, I think, from this line of work is that we combine, we look at what the theory can predict in terms of ratios of amplitudes between the modes in these combinations of three signals, and then compare that with what we can observe, and find that there's quite some overlap between these specific regions. So these amplitude ratios of mode triads can offer some constraint with respect to with respect to the amplitudes that we can observe. In summary, we have our result, and we can say that we have generated consistent variability models for a large sample of Kepler SPB stars. We then use those models to find nonlinear candidate resonances in most of these SPB stars measured by Kepler. We then derive the characteristic effect of an internal magnetic field on the gravity mode frequencies and determined when that effect should be detectable. We derive the governing equations and the time-independent solutions, which are important to then describe our observations, and found that the ratios of coupled gravity modes can offer some nonlinear insight into mode driving. Okay. And I think I need to actually let Michelle. I'm sorry, Michelle. I hope it was all understandable. There were some issues here.
The end of your presentation.
This was the
I could follow. No problem.
Now let me open the discussion. Remind you what the procedure is for this year. The candidate, Jordan Van Beeck, already had a discussion with the jury behind closed doors. This is an in-depth discussion with questions over his work. So that you already had a chance to ask many interesting questions. The purpose of the second attempt is to follow up on some subject matter, and it's open to the public and also ask questions. First of all, we introduce the member of the jury. We start with the supervisory team. In this case, it was another larger supervisory. We have Professor Tony Arts from the Institute of Economics. And Professor Tony University of Newcastle. We also have Dr. Timothy Barret from the Institute of Economics and Professor Ron Kaplan from the Center for Mathematical Plasma Physics. And we also from the Power. But we also have a couple of external members. We have who were present at the first events and now connected online. We have Professor Jim Fuller from the Theoretical Physics at the California Institute of Technology, United States. Good morning, Jim. And we have Professor Schmitter from the Institute de Recherche en Physique et Planetologie of the University of we start with the members of the jury who are far further away. So I give the word to Chancellor for the first question. Please.
Okay, choose themselves.
Yes. Going to unmute you.
Yeah, he needs to mute himself apparently.
You're still muted. Yeah.
I'm sorry, there's a little bit of a
Okay. No.
We can't hear you. Just a second. I must be on my side now.
Can you try to say?
Sorry. I can't tell what we're doing. There's an echo kind of thing.
Yeah, there's an echo.
Michelle, can you try muting?
Can you hear me?
Yeah.
Let me try to read you first. Okay, do we now have an echo?
Yeah, that's better.
Much better.
Okay, then Jim, please the word to you.
Okay, so Jordan, I have a question. You spoke mostly about SPB stars, which are gravity mode pulsators, but I think a lot of this physics could apply or be modified to apply to pressure mode pulsators, like beta Cepheid stars. I was wondering if you've thought about, well, I guess I'll ask first about the nonlinear coupling, how those processes would be the same or would be altered if you applied your analysis to those types of stars.
Okay, so the main thing I'm thinking about right now is how applicable the amplitude equation formalism would be for these pressure modes, because one of the assumptions that goes into the equation formalism is that the driving rate or the damping rate, for that matter, is very much smaller in absolute value than your mode frequencies. And I'm not sure how well that would be applicable for pressure modes. Otherwise, I think the formalism is not specified to a specific type of mode and is quite generic. So if that assumption, this amplitude equation validity criterion, as I called it in my work, is satisfied, I think we can use it also to look at couplings between pressure modes.
Yeah, I think you're right. How about the influence of the Coriolis force, which is very important for gravity modes? Do you think that would be important for pressure modes?
That is much less important for pressure modes, in fact, because their frequencies are higher than well.
Yep.
Yeah.
So what would be important then in terms of rotation?
If we are talking about pressure modes, we also have to talk about the outer layers of our stars. And depending on how rapidly you are rotating, these outer layers of your stars might not be well modeled by our one-dimensional models, which do not take into account any flattening of your star. So I think we might, depending on the rotation, we might have to upgrade our models.
Good. Yeah, I think I agree with all that. That sounds like a tough problem befitting of a postdoc study, maybe. Okay, so what about magnetic fields? How do you think those impacts of magnetic fields would change for pressure mode pulsators?
Okay, so for pressure mode pulsators, well, it depends on what magnetic field model you are using. The one we were using in our work was was quite was strongest close to the core. So so the gravity modes, which were very sensitive to that specific region, are therefore affected very strongly. Whereas if you would have modes that were less confined to that near core region, of course you expect the influence to be on the frequency to be smaller. But then again, if you look at other types of stars, your magnetic field is formed in a different way. You have your, for example, the field in the tachocline of the sun, and there you can then expect a stronger effect on your pressure modes that are propagating in the surface medium, well, near the surface.
Yeah, so where do you think, well, there is a certain type of star where magnetic fields are very important for altering the pressure modes. Do you know what those are?
Not right now, in fact.
The Rho AP stars, have you heard of those?
True, yeah.
So I'm just curious if you applied some of this analysis to magnetic fields, I guess, do you know where the magnetic fields are most important in terms of their interaction with the modes for those kinds of stars?
Well, no, I don't know where the main interaction or where the strongest parts of these magnetic fields are located inside OAP stars, in fact. No, not by heart, sorry.
Well, I don't understand them very well either.
Oh.
Yeah. I think the magnetic fields are most important near the surface because that's where the alpha and frequencies get much higher.
That is also true.
Comparable to the mode pulsation frequencies.
Yeah, and then you have a very strong effect.
Okay, so one last question. You showed the plots of your computed daughter mode amplitudes compared to parent mode amplitudes, and you also compared it with the observed. Yeah, so this plot has changed since your
Yes.
since the last version we saw. Can you explain what changed?
So what happened is that the way I selected these. So what has changed? The observational part has changed, and the theoretical part, I guess, right? So the left-hand side is the observational part, which was originally present or shown in this figure at the internal defense, and that has changed a little due to the fact that I'm using slightly different criteria to select these combinations of modes among the observed frequencies. That's the only thing that changed on that side. This was also explained, I think, on the page. Let me just double check. So how we select those modes is in fact explained on page 142 to 143. So we select the values of combinations that contain the two highest amplitude signals, and this is a new criterion. We select only those signals for which all of the single noise values are larger than 5. Otherwise, this selection criteria have not changed. On the other side is a plot which you've not seen before, well, but not at the internal defense. And this is basically showing you what the predicted surface luminosity fluctuation, or the observable Fourier amplitude ratio, is in terms of, well, on the x-axis we have the minimum of the 3 frequencies of the modes that are in a specific combination of 3 modes. And these what in colors we then see those modes that so in black you have the modes that fulfill all stability and all validity criteria, whereas in orange we have those modes that fulfill all stability criteria and this amplitude equation validity criterion, not enforcing the isolation validity criterion. And then you also have, so those were actually in gray, sorry. And then you in orange you have these combinations that we can form among the theoretically computed modes that are fulfilling all stability criteria. So, yeah.
Okay, thank you, Jordan. That's all I have.
Okay.
Okay, thank you. I just realized, apologies, I forgot to introduce myself. I'm Cabral from the Institute of Nuclear Radiation Physics. And so I'll now give the word to Professor Ryuto from the University of Toulouse.
Hello, Jordan. Can you hear me?
Yes, I can hear you.
Can you hear me?
Yes.
Okay, thanks. Okay, so, well, I have only very general questions since the technicalities, we discussed them before. My first question is, of course, about these amplitudes that you studied and the amplitude equations in particular. And I was going to ask you if we are able to predict these amplitude and in particular the ratio of amplitudes between modes what will we learn on the stars?
Okay, so these amplitude. So these amplitude ratios are in fact very sensitive to the rates at which this specific mode driving mechanism is putting energy inside your mode. So it's drive how fast your mode is driven and how fast your mode is damped. And so these ratios are in fact ratios can be written as ratios of these specific mode driving and damping rates, as well as the mode frequencies. So if what we can get from such amplitude ratios, if they would match with observations, and the other pattern that we can the G-mode patterns that we make are matching well with those observed, is that we can maybe try to predict what these driving rates are observation and damping rates. Another thing that we can do is play with different formulations of the opacity inside these stars, so the absorbing power for photons or light. And if you have different opacities, or at least different opacity gradients inside these zones where the modes are being driven, then you would also have different amplitude ratios that would be predicted, and therefore maybe we can have a look at the role of opacity within this whole well, it should be looked at the role of opacity within this whole framework.
Mm-hmm. So you say that when we try to match the amplitudes and their ratios with the observed one, what we would learn is the opacity profile, basically, in the star.
Yes.
Okay. And so the reciprocal question is, when you studied these amplitudes equation and applied to the stars, what can we learn on the dynamics of these systems? I mean, you see that the star is a complex object, and you model them with these amplitudes equation, but then the way the star realizes these these oscillations can teach us on the coupling and things like this. And so my question is, what kind of new physics can we learn from this comparison between observations and theoretical models?
These modes are of course very sensitive to these conditions in the near core region. So if you would have, or if you would add additional physics, such as let's say a differential rotation profile, what can we? These amplitude ratios. No, walk into a corner. I don't want to walk into.
I don't know if you hear me. Maybe my question is a bit too ambiguous, but to make it more precise, when you studied this amplitude equation, you considered several scenarios, for instance, of the coupling between modes, of the instability of modes. And so when we observe, when we have the data, can we select one preferential scenario of the coupling on the way modes are excited and damped and limited in amplitude? Or say the observations say that, well, there are many of them and well, all are active, and well, we will interpret only the simple ones. You see.
Okay. So within the formalism, the amplitude equation formalism that was developed in chapter 4, we look at which of these specific interactions of tree modes are in fact producing these time-independent solutions that are valid and stable to small perturbations around their equilibrium values. What we can say, if we can match one of these theoretical amplitude ratios with an observational amplitude ratio, is that there's a good chance or there's high likeliness that this specific mode combination of three modes is in fact well generated by the energy exchange among these modes in our theoretical model. Now, of course, this specific graph was made taking into account a specific interaction between specific modes, it's showing you a specific part of the amplitude ratio diagram, let's say, that can be used to explain these specific interactions. But I think what one can do is make more of these diagrams and try to populate the entire amplitude ratio frequency range to try to have an idea of whether these specific three-mode interactions are important, or whether we need even well, different interactions between more modes.
Okay. My last question would be, what would be the most promising follow-up of your work, in your view?
Okay, so right now the most promising follow-up is trying to exploit the formalism as it is to specifically model one of these stars for which we have a robust model of the variability defined in chapter 2, and then try to match up these theoretical amplitude ratios with some of these observed ratios, because what we see now in this graph is in fact an ensemble of all these different signals that are obtained for all these different stars that we looked at. And when we do that, we also should take into account the effect of an opacity table and try to get a better grasp of how these opacity gradients are inside these mode driving zones for one specific star or multiple.
Okay, thank you.
Thank you. Now we continue with another present in person. Give the word to Mr. Kaplan.
Okay. Jordan, let me start by congratulating you once more. I think this is a real piece of work, this thesis, that goes from handling advanced data and actually, making solid conclusions out of it. Also, a lot of theoretical analysis that you combined. You made also numerical tools that will be useful not just for you, but also for your colleagues. So again, I mean, this is something that you are, I hope, and you should be proud of. So that said, as you know, I have some questions. And the reason is that because you really make links with work that I do. In the sense that once you start quantifying magnetic fields, you come into the realm of magnetohydrodynamics, and that I find an interesting topic. So let me make you a few general questions. Part of your work, especially where you, let's say, talk about the effects of magnetic fields on the G modes in your case, in that part you're using the linearized equations. And then you go to your next chapter, and still here, where you actually then extend it to, like another order, literally, you add, and then you see how modes can couple. Now, today we have like enormous supercomputers, so why don't we just solve it nonlinear? I mean, what's holding us from doing that fully nonlinearly? And how long do you know how long these, let's say, these coupled solutions that you found as sort of steady, resonators, or how do you call them? Would you expect them to persist even in full nonlinear simulations?
Can you hear me? Okay. So to answer the first question, so what we also try to do, in part of the chapter 3, where we consider the magnetic effects, is of course try to get a sense of the effect of the evolution of a star, right? So even I think with the best supercomputer we have available right now, we cannot simulate over the entire main sequence. This would, some stars take billions of years to evolve down the main sequence, and I'm not sure how long it would take to evolve billions of years on a supercomputer, but I know that it takes quite some time to evolve for some physical star hours on a supercomputer in full magnetohydrodynamics, and I think these are also the nonlinear magnetohydrodynamics equations that are being solved. So in that sense, I hope you still agree with me that there's some premise in using some simplified versions of that.
No, I fully agree with this. Yeah. And also, indeed, I have a similar interest in even the linearized equations, where I now notice that you indeed agree with me that Freeman and Rothenberg were already on this kind of topic a while ago, even before I was born.
Yeah.
And that there is quite some knowledge as to how even linear oscillations of magnetized plasmas actually know about the orientation of the field.
Yeah.
So in that context, let me ask you again, the orientation, the topology of the field that you assumed in the chapter where you talked, what is that exactly, and how would your results there be influenced if you were to vary that topology?
So the topology is that you would have a strong field as a strong magnetic field as a torus around your core, and then a weaker part that is poloidal in most and that is mostly so the magnetic field is also inside the star. We do not have any field lines that exit the star as well, which is and we also have in chapter 3 at least, we have that field align with the rotation axis. So one of the things
I was going to ask you this, and so you do your linearization around an equilibrium, right? And you admitted that right now you assume a one-dimensional equilibrium, but everything you just talk about actually is not 1D. Right? So in the sense, I was wondering, there is this concept of if you really want an axisymmetric 2D equilibrium with rotation and magnetic fields, essentially the ingredients you're interested in, and you want it to be a stationary solution to the set, then one of the equations will tell you that there is a tight coupling between the flow, the poloidal and toroidal flow, and the poloidal and toroidal magnetic field component. It's technically called the isorotation web of Ferraro, but I mean, in that sense, the fact that you use this assumption that your field can, for many purposes, be ignored, but somehow you take it along, right? Can you explore, say something a little bit more about that? Where would that assumption break down? When would you have to take this isorotation law into account?
Okay, so I think that would have to be taken into account when your modes are nearing the alphane frequency. I mean, and what we now do is select a region of modes that are not close to the alphane frequency.
In fact, I was going to ask you exactly that as well. You talk about P modes and G modes.
Yes.
And I'd say from the MHD perspective, but not just me, we talk about slow, alphane, and fast, and you just mentioned the alphane waves. And so even if I were to do seismology here in this room, where I can, let's say, assume a horizontal field, then I would talk, actually my fast would be what? The fast, the slow, and the alphane versus the P and the G. Do you know where they relate?
In terms of, hold on.
Well, I'll tell you that there will be two types of Gs. There will be G alphane and G slow. And so I was curious, is that something that, on which family do you relate to? Do you actually, can you pinpoint that, or is that something that you still have to look into?
I think I have to look into it, but I have a feeling that it's a G alphane. But
and another thing that you nicely explained is how you have these quantum numbers, right? and so in I guess the basic stuff about quantum physics, I'm not very familiar with it, but I know that there's an electron that is only on a few orbits. It's bound to its core, to the core, and so there are these discrete levels. But then when the electron is free, there's a continuum, right? So we discussed this earlier, also in the pre-defense. Whenever you have a radial variation of whatever quantities, your alphane frequency changes with radius. And so from the MHD perspective, there are continuum bands where all the frequencies within a certain interval are actually solutions. And so I'm curious, this labeling of the period changes, has you changed the radial number, right? I mean, how would that show you that there all of a sudden would be a continuum range? Did you think about that? Is it something that you would see as something that wildly oscillates, or that goes up or down? Or, I don't know. I don't know the answer, but maybe you might.
I'm not. I'm not really sure right now.
But similarly, in MHD and also in quantum, you know that there are also mathematical properties in terms of the ordering of frequencies. They can be Sturmian or anti-Sturmian. And so, how is that seen in these delta P versus periods talks? Is that something that you can?
Okay, so if I recall correctly, if it's anti-Sturmian, you would have a downward slope.
And so the fact that some of your things are actually oscillating, is that going to tell you that I don't know, there's some interesting frequency range that you hit? Or?
So the oscillations in these patterns, they can be attributed to, well, they are generically attributed to, or typically attributed to the what is happening in the boundary layer. So if you have, if you evolve your star, you would have a depletion of hydrogen because of this overshooting, and then you would have a specific gradient start to build up, and then because of that buildup of that gradient, then that would be linked to the amount of dips that you also see in your period spacing pattern.
Thanks. I also looked at your appendix. That's something we didn't discuss during the, and so I thought, well, why don't I ask a question there? Because this is the first appendix. You talk about your LM fit and your method, etc. And so this is something that you made, right, or you use, or you have adapted.
We use it.
And so one of the things that you say there on page 155, it says, so at some point you need to quantify a Jacobian matrix. And here it says you estimate it by a forward difference approximation. And of course, that's fine. But is there any reason to go to a higher order difference, like temporal difference or whatever?
I did not experiment with other methods of computing the Jacobian, but I mean, it's a fast method for sure. It could be worthwhile to maybe also try to see how your Jacobian matrix might change numerically. I don't think there would be any numerical issues, but I don't know.
Yeah. Good. Thanks. And then about your so your I guess your crowning piece of work, I think, is the one with all the derivations of your nonlinear couplings, etc. And so we you got these questions before also about you said what you show here is of course assuming some specific set of specific parameters and specific models. But then the questions that were posed by my colleagues and myself also is, but these equations, maybe they cover more than the specific case that you did. Can you now are there analogies in other fields of physics where these kind of resonator models also play a role? Are they being used in similar way? Can you, on the basis of your solution that you showed, tell a laboratory experimenter to say, okay, why don't you tune something here and there, and then you will see this? Is that feasible at all?
In principle, we can do that with coupled springs, for example. I'm not sure what the application necessarily would be, but yeah, that's really fun to watch. Yes, I agree. And I think also, well, like you mentioned, Freeman and Rothenberg came up with the formalism, so there are also accounts of nonlinear mode coupling in magnetohydrodynamics that were being covered. I don't know the name of one of the studies I had in my mind right now, but
thank you a lot for
thank you.
Your thesis and for our discussion.
Thank you.
Thank you. Now the word to Dr. Van Beeck.
Jordan, let me also start by congratulating you. You've done quite a bit of work that we, at least I, as an observer, as an observational astroseismologist, rely on, but it is so complex that I'm very reluctant to tackle it myself, so I'm very grateful that you've done it for me. I have prepared a few questions on the figure that you're showing here. However, both Jim and Michelle have already asked questions that answered, or that led to the same answer that I was going to ask for. So let me take a step back. Before, I've asked a lot of questions on how I can use your work to look for, or to model our observed stars. So on this occasion, let me ask the opposite question. In future, if I observe a star, if I model a star, using simple linear astroseismology, what quantities do I need to report to make your life easier? If you want to extend your framework, if you want to continue building the nonlinear astroseismology framework, because right now, if I look at a pulsation, what I often only report is frequency, amplitude, phase, sometimes combination frequencies, but that's it. What else can I do to make your life easier?
So I should assume that you also report the amplitudes and phases and frequencies and phases only of non-combination frequencies, right?
Yes.
So I would very much appreciate it if you also do it for the combination frequencies. And otherwise, yeah, I mean, the framework itself, the computational framework itself already looks for combinations between lists of these parameters. So there's not much more that I would need, I think.
Okay. One of the things that we do as observers is we are very set in our ways. So, yeah.
Rotation frequencies would be useful as well.
Okay, rotation frequencies, that we can do. But I was even thinking more like observing, as I said. Sometimes, and you do it in your work as well, sometimes we express pulsation amplitudes in linear units, sometimes in logarithmic units, in magnitudes. That means that if you look at parent frequencies and total ones, the amplitude ratios will change. What do I do? Do I continue working in magnitudes? Do I swap to linear units?
I would think that linear units would be preferable, but I'm not 100% sure. I think, well, yeah, I'm not 100% sure actually. I need to think about this. I think my first thought is that the linear units would be the most useful for computing these amplitude ratios.
Okay, and on a related note, sometimes we express pulsations, or we fit sometimes to measure the observed pulsations, we fit sine waves to our knot curves.
True.
Sometimes people prefer cosines. Now for the amplitudes and the frequencies, that doesn't matter. It does for the phases.
Yeah.
Which do you prefer?
The ones I was using in my framework were sine waves, but it's pi over 2 offset, right? It's not necessarily a big problem if you supply me with as long as I know whether you're using cosines or sines in your model, it's okay. I can handle that, I think.
Okay, so note to both myself and all observational astroseismologists listening online is report whether we're using sines or cosines.
Yes, please.
Okay. And in the linear astroseismic modeling, are there specific quantities that we should include in our models?
Yes. So I also in the appendix, I don't remember which number, there is a specific procedure to compute a adiabatic derivative of gamma 1. So if you are, for example, using MESA models for your astroseismic modeling, I would very much like if you would also include that procedure in your run star extras. That would make my life a whole lot easier to compute some of the coupling coefficient, some of the terms in the coupling coefficients. Thank you.
And then again, a related question, but moving more towards non-existing work, you've applied your framework to the available data, to stars observed with Kepler, because that's what we currently have. But now we also have TESS in future, we have Plato. What other observing campaigns can we or should we set up to test the results that you find?
Mm-hmm. So Kepler was very useful because it provides you with a very low frequency resolution so that you can pick out individual waves, which you wouldn't be able to pick out if, for example, you observe a star for a shorter amount of time. But even Kepler, had the issue that sometimes there are modes or at least signals that are so closely spaced that even the Kepler frequency resolution is not able to resolve them. So it would be well, there are. And I'm not going to ask for an 8-year observing mission, but longer time baseline would help with resolving these individual signals, and then also help with characterizing the amplitudes and then your frequencies of those signals. So I think I think that would be the main that would be nice.
And the last question about it. Okay. And what about wavelength dependence? So Kepler was mostly in the visual passbands. This was a lot more red. For those future missions, for the future observations, would you prefer a different passband? Would you like it to match Kepler? What would do the most results?
Of course, it would be easiest if the passband matches that of Kepler, so that we can directly, in principle, compare. That we compare with less systematic uncertainties, let's say. We can perform the comparison with less systematic uncertainties, so I think also different modes might be observed if we go to different passbands. So maybe multicolor photometry might even be an interesting option to explore for future scientific endeavors.
Okay, thank you.
Thank you. The promoter supervisors want to ask a question. Yes, of course you can.
Hi, Jordan. So again, yes, let me congratulate you on this great work. It's been a pleasure to work with you on this, more on the observational side where my skills originate. I want to push you outside of your comfort zone, right? So I agree with all your conclusions, but I'm very biased, so that's okay. But when we look at pulsations in intermediate mass stars, there's this, to first order, this relationship that as the amplitude goes higher, the nonlinearity of the star is more important, right? Mm-hmm. So we see this in Delta Scuti stars, the Cephids, the Aureliris, for example, which are P-mode dominated stars. Mm-hmm. But you've been working on G-mode dominated stars. Mm-hmm. Do we see the same relationship between amplitude and nonlinearity?
I would certainly expect to see it, given that you would have or would need your mode to at least have some amplitude that is over a specific threshold in order for this mode energy exchange to occur. And if you then so hold on. I'm confusing myself right now. for a second.
Well, would you say that for the higher amplitude SPBs in your sample, there are more combination frequencies on average compared to the lower amplitude SPBs? Is that a correlation that you can tease out of? I know it's a very small sample, but can you tease that out of the data?
I actually am not sure if that is a correlation that we can get out of this sample, because I know that there are specific stars that have lower, quite, well, relatively low amplitude modes, let's say, that for which we found many combinations actually. Whereas that is not the case. Well, we have some other stars in our sample that are, of course, non-sinusoidal, they're outbursting, and then these have typically large amplitudes, and we even in those models we find some combinations, but there's a limited amount of sinusoidal combinations that we can get out there. And some other high amplitude stars, I think, do not have that much combinations compared to. So I don't think there's necessarily a correlation in our sample with regards to amplitude and the amount of combinations we find. The question is whether the combinations we find can then be explained by these theoretical models, of course. Maybe it's a different mechanism that is forming these combinations that we find.
So I'm also curious about your feeling, opinion, conclusion on some sort of mechanism that seems to limit the amplitude of the G-mode to the surface, and this is in some cases 2 or 3 orders of magnitude to the maximum P-mode amplitudes that we see in some stars that are very, very similar in mass and age to the sample that you've looked at. Mm-hmm. So what's the physics that you would investigate on this amplitude limitation mechanism? And is this an extension of your methodology potentially you can work on in the future?
So I'm it's not entirely in the image, but the main at least model parameter that I need to vary in the future is look at how different opacity tables affect the results and affect these amplitude ratios. How that specifically relates to observations is, well, yeah, it would match different parts of the observational ensemble on this figure, but yeah, it depends. It depends on what we find in the stars that we would work on.
So do you think high amplitude SPBs with pulsation amplitudes of up to 0.1 of the magnitude exist?
I would think that they would somehow be limited by some nonlinear amplitude limitation or absolute saturation mechanism before reaching that amplitude.
I tend to agree, and I think that emphasizes once again why your SPB sample is very, very important to keep working on. Yeah. There's a clearly distinction from the P-mode dominated stars. Yeah. Thanks.
Okay, thank you.
Okay, thank you. Now the floor is open to the public for questions. Don't see any, but I see one online.
Yes, hold on.
Yes.
So this one?
Yes, that one. So most of these stars are in binaries. Is there a reason why you did not consider tidal excitation in G-mode? Maybe you can say something about the samples that you chose.
Yeah. Okay. So these specific SPB stars that we looked at in this sample are in fact mostly single stars. I think there are 2 binaries that are included, and they are not close binaries. They are I don't recall their periods exactly, but they are not close by binaries, so that tidal excitation is not necessarily something we would expect for these specific binaries that we still have in our stars. So that's basically why we did not consider it in our models, but in principle, formalism is generic. It's a tidal excitation term that we should add on the right-hand side. It's I make it sound easy, but it's not. But yeah, so yeah, it would be exciting to work on that.
Okay, thank you. So if there are no more questions, we close the discussion here and we go for deliberation.
Okay, so.
by obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in ALEA European Code of Conduct: reliability, honesty, respect, and accountability. I hereby close the session. Congratulations.
Yes,
28.
28 indeed. Three.
That's good. That's fine. Give the word to Mr. Provider.
Are we still online?
You are normally online, yes?
Okay.
And you should have sound now. I accidentally muted you while you were reading out the.
Sounds like we have sound.
Yeah.
So, Jordan, Dr. Van Beeck, congratulations. This is a very important milestone. I hope you're very proud. I'm certainly proud. This is a great accomplishment. And certainly to get a PhD from KU Leuven, a prestigious university, is not something that many people have on their CVs. So congratulations for that. It was during your master's in astronomy and astrophysics that we first met. And you had the unique ability to request a certain thesis, which is the first time that's ever happened in my career so far, that a student had the initiative and the ambition to ask for a difficult topic as their master thesis. But of course you succeeded, and that, I think you were inspired by Professor Fuller's seminar, correct? Right, good, I got that right. On magnetic fields, and that really was the synthesis of your master thesis that led into your PhD thesis. So that's a good testament to Jim inspiring you, and then Connie taking you on as a master student to do that difficult work and succeeding very well. Of course, that was with Timothy as well, as a co-supervisor of your master thesis, who's here today. I'm very happy to see him as an internal examiner of your PhD. So you also got a publication from your master thesis, which is also something not everyone has on their CV. So this is again a good accomplishment, of which we're very proud of you. And you know this because I've said it very, very many times to you, that your PhD in particular was extremely ambitious and the very testament of high risk, high gain, as the buzzwords often require us to say. I think you had something like 7 work packages originally in your 9-month defense, which is about a factor of 2.5 more than what I have when I write a project. So again, testament to your ambition. Now, of course, COVID was ever looming during your PhD. You were perhaps in the worst PhD cohort possible, having started about 6 months before the first lockdown. But you succeeded in that high risk, high gain plan to combine magnetism and nonlinear astroseismology. We dropped the binarity. I think you agree that was probably a good idea. But again, Jordan has this wonderful attitude to trying to solve the universe. And partly my job is to try and rein in a little bit to solve at least our part of the universe before we do the whole universe. But that's a good thing, I think, to have that sort of curiosity and ambition. Now, you've also come a long way in what I call the soft skills. I hate that phrase, but I'll call them soft skills, as well as the technical and the numerical side of the PhD. So the presentation and the communication skills, I think you'll agree that this has come a long way. And I'm very proud to have been on the journey with you to get to this day. And I think I wish you all the best for the future. And I hope that you look back fondly on your memories at KU Leuven, especially now since I left. I think it's a good time to leave as well, right? Congratulations, Dr. Van Beeck. You can have a memento of your time, which I expect you to be wearing forever. And then
Misschien kan je de cadeautjes op de receptie doen.
Ik denk dat dat een idee is.
Ja, Jordan, hier staan we dan, hè? 6 jaar ongeveer nadat ik op de gang naast auditorium 0511 een nerdy persoon zag staan. Die mij verlegen in het aanvaard vroeg. Dat bleek dan schotels te zijn, dat wist ik toen nog niet. Ja, zou dat wel haalbaar zijn? Ik heb een master in de chemie en ik zou graag een master in de sterrenkunde doen. En ik weet niet of je nog weet wat ik toen geantwoord heb, misschien toch niet zo goed. Ik heb toen gezegd dat dat zeker mogelijk is. Niet gemakkelijk, maar wel mogelijk, afhankelijk van motivatie en drijfveer. Dat was mijn antwoord. En dan ben je er maar aan begonnen. En ik herinner mij ook jouw eerste examen bij mij. Stellar Structure and Evolution. Ik vond dat niet geweldig. Dat was eigenlijk, met excuses voor de chemici in de zaal, nogal een warboel van gekriebel. Ja, onnodige details, waarin ik de juiste antwoorden die er wel ergens stonden, zelf moest zoeken. Ik heb daar een opmerking over gemaakt. Ja? Jij komt weer. Chemici communiceren anders dan sterrenkunde. Dat is nog altijd zo. Hè? Dat is nog altijd een werkpuntje, hè? Ja? Dus hou het in de mond, om het op zijn afdeus te zeggen. Okay. Maar de motivatie en drijfveer, die was er wel. En dat is toch wel belangrijk. Tijdens een maandse workshop heb ik jou ook gevraagd van, waarom heb je eigenlijk chemie gestudeerd? Ik weet niet of je dat antwoord ook nog weet. Ik wel, dat is nou bijgebleven, dus ik ga het nu voorlezen. Omdat ik dacht dat ik de wiskunde en de fysica niet ging kunnen. Tot zover de motivatie voor de chemie. Ja? Wij weten ondertussen dat je goed bent in wiskunde en dat je graag wiskunde gebruikt om fysica te leren. Soms een beetje te graag, dat manier van spreken. When we started with English, you were one of the 2 master students actually to hook on to Dominic's style, who voluntarily indeed attended the seminar by Jim Fuller, who could not stay on, but he knows what I'm going to say. And that was, I still remember the date, it was 21st March, the beginning of spring in 2018. So it was the beginning of spring that year, but also the beginning of your role for magnetism inside stars. So that's where we got it. So I wanted to take this opportunity to thank Jim. I did it in the deliberation for being an inspiring lecturer for you. That was certainly the case and still is, and for hosting you at Caltech for these 8 months, despite harsh times during the pandemic, which you suffered a bit from. We all did, but you certainly also did. Jim certainly triggered your interest to make a PhD, and then came Tim. So it was Jim and Tim. Because also Tim inspired you with his lectures on the theory of stellar oscillations, along with Dominic. Dominic came along the path, along the road to help you with the observational aspects, and also the communication aspects, I want to say. So, speaking of which, communication. I remember that Dominic, as a native English speaker, had trained so hard to pronounce Jordan op zijn Vlaams. And then immediately after that, you firmly told him that you wanted to be the American pronunciation. Very firmly. Well, Dominic, thanks for coming back to this session from the UK after being only 1 month as a professor in your life. That's linked to your career as well, because we haven't had a chance to do that. but let me move back to Jordan now. And so Jim and Tim, make the chemists want to embark upon a theoretical PhD in non-nuclear astroseismology. What an idea. Huh? Rather than some topic that you may have thought when you were first asking me if it could be possible, I think you had somewhat in mind to do some kind of astrochemistry topic, which would have made sense, right? But no.
Jordan, ik herinner me nog heel goed dat je les kwam volgen bij mij, zoals iedereen hier. Je moet wel indruk gemaakt hebben. Maar anders dan bij Connie was je examen bij mij al wel direct top. Je moest bij mij een aantal oefeningen maken, een project maken en dat was echt iets waar je je direct in kon uitleven op je eigen kenmerkende manier. Ja, met veel, moet ik zeggen soms te veel, zin voor detail en voor interessante uitwerkingen. Toen Connie me vertelde dat je een chemicus was, kon ik het eigenlijk moeilijk geloven. Hoe kan dat nu dat een chemicus eigenlijk een betere wiskundige en fysicus is dan de meeste wiskundigen en fysici? Ik wist niet dat dat bestond. En dan hoorde ik nog dat je dacht geen studies wiskunde of fysica aan te kunnen. Nu, ik hoop dat je van dat waanidee toch verlost was toen je besloot om je thesis te gaan maken over niet-lineaire asteroseismologie. Ik denk, Jordan, dat we het er eens kunnen zijn dat we een aangename en ook leerrijke reis gehad hebben, waarin dat we regelmatig elkaar uitgedaagd hebben om met de juiste verklaringen naar voren te komen voor al die resultaten van je toch wel dikwijls zeer ingewikkelde berekeningen. En een reis ook waarin dat je me meerdere keren eigenlijk verbaasd hebt doen staan over de snelheid waarmee dat je soms toch die moeilijke berekeningen kon maken. Maar soms was ik ook verbaasd over je volhardendheid in het controleren van iets minder de zaken doende feiten eigenlijk. Ik moet je ook nog bedanken omdat je een lange tijd toen je in Californië was, 's morgens vroeg wou opstaan om online te vergaderen, zodanig dat ik toch nog een rustige avond kon hebben. Nu, dokter Van Beeck, proficiat. Je bent nu een echte sterrenkundige. Dus ik wens je nog veel succes in je verdere onderzoeksloopbaan.
Thank you. Let me move back to English a bit. I also wanted to take the opportunity to thank Michel Vitor. Also, he's no longer online because I think he's somebody who's very interested in non-linear coupling, and he has an immense passion and knowledge of astrophysical fluid dynamics, which he has already sort of been transposing upon you during the internal defense, and we will benefit, I think, from him for our joint synergy grants for this topic. Tot slot, ik wil een woordje van dank richten aan de familie en de vrienden van Jordan, om hem uit het verre schoten naar Europa te sturen. Eigenlijk is dat een beetje grappig, want ik heb eigenlijk pas in de loop van jouw studies ontdekt via mijn vrienden, Rudy en Frida, wie jij eigenlijk bent. Ja? En dus dat is, je noemt jezelf de chemistry dude. Sorry, maar dat heb je zelf in je boek geschreven. Hè? Ja, die chemistry dude op de gang, dat is eigenlijk, had ik daar sneller kunnen weten wie dat was, als je mij zegt dat je de zoon bent van Nancy Bormaas. Ja? Want ik wist dat ik getrouwd was met een Amerikaan, ja? Een zekere Roger Van Beeck. En dat is een insider tussen ons, die het publiek niet snapt. Maar soms is de wereld echt heel klein. Ja? Ik heb begrepen dat dochter Van Beeck vorige week gehuwd is. Ja? En zoon Van Beeck vandaag dus gedoctoreerd. Dus proficiat aan de familie. Drukke feestweken zijn dat. En ik stel voor dat we daar nu alle samen van gaan genieten. Ik ga je nog even blijven doordrillen, Jordan. Hè? Op kosten van de ERC. Nog een korte tijd, nog wat werken aan je zwakke punten. Gaan we samen doen. Maar nu gaan we eerst feesten. En dus van de twee promotoren, van harte proficiat. We hebben samen een cadeautje voorzien. En dat moet je dan ook nog tijdens de receptie openen. Dat zijn hopelijk zaken die je wat helpen ontspannen. Van harte gefeliciteerd.
Okay. I honestly did not prepare a speech at this time, in this short occasion. So I will also keep it short. I would like to thank my wonderful promoters for the pleasant atmosphere that we've had during all of our discussions. And I thoroughly enjoyed working together with you. Might not have always received it, I don't know. It was, I'd say, let's go like that. Yeah, I think that we could not have done it with another, in another setup, the work that we did in these 4 years, in my opinion. I'm not a great speaker, as you can tell, but I promise you there will also be a wonderful reception waiting on you in a few minutes. Well, I hope in a few minutes at the cafeteria in 200D. So, without further ado, let's try to enjoy the reception. I have a gift. That's true. I have a gift.